Okay, so welcome to our continued discussion on trying to understand particle dynamics at very low Reynolds number when viscous effects are important. And we have systematically been looking at especially one class of problem, which is a translation of a particle. So, we set out doing this problem the first time we studied this problem in the Stokesian limit, which was basically saying that the inertial terms are absent and we have an instantaneous balance between pressure gradient and viscous force. Then we move to the scenario where we said that this particular problem is singular in nature. So, by singular in nature what I meant was, if we focus on the steady problem, then the steady problem is a problem where if I say that inertial effects are weak, which is quantified by a Reynolds number based on the translational velocity, the length scale of the object and the kinematic viscosity of the fluid. If this is a small parameter, there is going to be a region in the flow beyond which you cannot consider inertial effects to be negligible. They are as important as the viscous term. So, we went through various ways of arguing this. So, this is effectively aspects of the advective inertia being non negligible. So, today's class we are going to dedicate some time trying to understand the importance of unsteady effects. So, Stokes flow, when we started discussing the problem, we discussed the aspect of linearity, we discussed the aspect of reversibility, we also discussed the aspect of a quasi steadiness. So, quasi steadiness effectively means that if I have a spherical particle, or it could be any particle for that matter, and it was moving with a velocity u1 at time t equals 0, and then at time t equals t1 I suddenly switch and increase its velocity to u2. Now, if I ask the question that what would be the drag at time instant t2, which is beyond some time instant t1, you will immediately come back and say that the drag force that it is experiencing is minus 6 pi mu a u2. So, if I were to place a time here in the problem, the drag force at any instant of time is the drag force based on that instantaneous velocity of the particle. So, you could do this particular behavior where there is a sudden switch. So, here if I were to plot the particle velocity, it remains as u1 and then it jumps to u2 at t equals t1. T is the time axis. Now, if you instead set about increasing its velocity from u1 in a linear manner and then hold it fixed at u2. So, it is constantly accelerating and then at time t1, so you choose the acceleration such that it achieves the velocity u2 in the time instant t1. So, then at a time instant t2, if I am actually trying to find the drag, it is going to be exactly minus 6 pi mu a u2. If I instead did a calculation or had a protocol where it went with u1, it decreased for some duration of time to let us say u3, and then at an intermediate time between t1 and t2 it accelerated and came to u2, the blue curve. Again, for this particular protocol, the drag force at the time instant t2 is all again going to be minus 6 pi mu a u2. This is the idea of quasi steadiness of Stokes flow. Or the idea of instantaneity. What was the idea of instantaneity? The idea of instantaneity was that viscous diffusion happens instantaneously. When you make a change to your boundary condition, the change in the boundary condition is going to propagate in the fluid through viscous diffusion, and this process is infinitely faster than any other process in the problem. That is at the heart of your steady Stokes flow equation. Today's lecture, we are going to focus on what is the contribution of the unsteady term. Now, this is basically going towards trying to write down what would happen for tiny particles which are governed by the full momentum equation. Now, the full momentum equation is obviously not an easy equation, because you all know that the full Navier-Stokes equation is a nonlinear equation, and you won't be able to solve this nonlinear equation analytically. You would have to solve this numerically. So, what we are doing, we are taking this approach of breaking this problem down into different pieces, with each piece being an improvement over the previous one. So, the Oseen flow equation was an improvement from Stokes flow with the convective acceleration being included. Today's lecture is going to be Stokes flow plus only the unsteady term. We are not going to discuss about the convective term today, and then later towards the end of the lecture we will try to basically get an overview of what each of these terms are doing. But right now the equation that is of interest is the equation which you could write it with rho multiplying it as the unsteady Stokes equation. So, just like your Stokes equation, this equation is also, what is the commonality between this equation and Stokes equation? It is linear, which means all the ideas that we introduced earlier, that when we are trying to work out the solutions are going to be linear in forcing, that continues to be true. So, first what we will focus on is what do we expect to happen with the inclusion of unsteady term. There is obviously an elaborate method of calculation for a translating sphere problem, and I will take you through some important parts of it and skip over the ones which are actually more of doing detailed algebraic calculation. But before we even step into doing a full fledged calculation, it is important to understand that what do you expect to happen when you include the unsteady term. So, if you take your motivation from the advective problem, the Oseen flow equation, our approach was, we said Stokes flow due to either a translating sphere or a sphere in a uniform flow, whichever one you wish to choose, gives me a disturbance velocity, that is the disturbance velocity scales as far away. If you are in the reference frame of the lab, it is 1 over r. If you are in the body reference frame, it would be some uniform flow plus an order of 1 over r term. Now, when we did Oseen flow, a small digression or revision of what we did earlier, we said the viscous term, which is mu del square u, this behaves as, how does it behave? What is the scaling of mu del square u if I consider the Stokes flow solution? You will take a second derivative of this term, right? When you take a second derivative, what happens? The 1 over r becomes 1 by r cube. So, this is actually 1 over r cube, and if you just want to be dimensionally consistent, there is a u bar a term that is present here, right. This is actually a by r. So, when you calculate the viscous force per unit volume, you take a second derivative with the radial coordinate twice, and that turns out to be mu u bar A by r cube. And then we said, what about the inertial term u dot del u? What is the magnitude of that particular term? So, the first term is an advection that could happen either due to the uniform flow or due to the disturbance. Now, the disturbance is weaker than the uniform flow far away. So, this advection is just u bar, and the del u gives me u bar A by r square. So, this is u, this is del u. Okay. Now, what we did next was we said take a ratio of these two terms, because that is the argument, right. This is supposed to be small. If I say weak inertia, this term should be negligible or it should be very small. So, if you take a ratio of these two terms, rho u dot del u divided by mu del square u, you end up getting a term that is rho u square A by r square in the numerator and mu u bar A by r cube in the denominator. So, when you cancel out all the relevant terms, you end up getting r u bar divided by rho r u bar by mu or r u bar by nu, which gives you a screening length, if I call that r star, that scales as the kinematic viscosity divided by the translational velocity, beyond which, so if r was greater than r star, you will have inertia competing with viscous forces. You cannot say that you are looking at a problem where inertia is weak, that is just not going to work. So, with this kind of an argument, let us see what is going on in the unsteady problem. So, I will again borrow the same approach, that if I consider a Stokes flow solution, the viscous force per unit volume scales as mu u bar A by r cube. Now, the unsteady acceleration is rho du dt. So, this should be rho u bar divided by a time scale. Now, what should be the time scale? You have a sphere that is translating with some velocity u and it has a radius a. So, if you say that the time scale, one choice of time scale is A by u bar, that is just saying how much time would it take for a fluid parcel to travel a distance comparable to the body size if it was being advected by the characteristic velocity in the problem, and that would be A by u bar. Now, if you were to make that choice and substitute for A by u bar as the time scale in the unsteady problem, you will end up getting a term which is rho u bar A by u bar, which is the same as rho u bar square by A. And this, as you can see, this is basically a measure of advective inertia, because you have said that the time scale is the time scale that is due to the particle trying to move with a certain constant velocity. Now, we are interested in an unsteady problem. Now, what kind of unsteadiness can you think of? So, we already drew few protocol here, right. There can be an unsteadiness where the particle is constantly accelerating or decelerating, or you can also have a scenario where the particle is executing some kind of an oscillatory motion. You have a spherical particle or you have any particle and the particle is basically doing a back and forth motion, an oscillatory motion. So, even though it has a velocity, so let us say the velocity of the particle is some u naught cos omega t. So, you can construct a time scale, you can construct two kinds of time scale. One time scale is the particle size by u naught. That is the time it takes for a fluid parcel to move a body length due to the amplitude of oscillation. The other time scale is 2 pi by omega. That is the time scale associated with the time it takes for it to change its amplitude. It is going through this periodic behavior. What is the time period of oscillation? So, when we are doing an unsteady problem, it is more appropriate to think of there being a separate time scale in the problem. It could be either due to the oscillation if you are doing a periodic problem, or it could be something else that is there where the particle has some kind of an imposed acceleration or deceleration. So, right now without getting into the detail of what that time scale is, I am going to write this as tau. Now, one aspect which you need to remember here, that the velocity that I am writing here, should this actually be the velocity which is the particle's velocity, or should it be the disturbance? Because u is u bar So, this scales as u bar plus u bar a by r. So, when I am calculating the acceleration, what is dou u dou t? Dou u dou t is the fluid acceleration. So, the acceleration that I am trying to actually calculate is now for the disturbance in the problem. So, dou u dou t is going to be u bar a by r divided by tau. It is the acceleration associated with the disturbance that it is creating. So, we are basically viewing all of this for the disturbance. So, this becomes rho u bar a by tau r. Now, let us take a ratio of these two terms, rho dou u dou t divided by mu del square u. Numerator is rho u bar a divided by tau times r, and the denominator is mu u bar a by r cube. So, you have r square by tau mu rho in the denominator. So, this is r square nu tau. So, this tells us that there is a length scale where if you were below this length scale, if r by r star was much less than 1 or r was much smaller than r star, what do you think would be happening in the physics? See, how did we arrive at this length scale? We arrived at this length scale by doing a balance of forces, viscous force per unit volume and inertial force per unit volume, or balancing the unsteady acceleration with a force per unit mass or viscous force per unit mass. So, what do you think is going to happen if you are within distances which are much smaller than r star? So, if I write this as r by r star whole square, right. So, if r is much smaller than r star, that means this ratio is very large or very small? This ratio is very small, which means that unsteady effects are negligible. When r is much greater than r star or square root nu t, that is when the unsteady terms are comparable to the viscous term. Why am I saying comparable? I am saying comparable because the assumption that I made to show that whether they are in balance or not in balance is basically taking the Stokes flow solution. So, for R greater than R star, the Stokes flow solution is not going to be a correct representation of the flow. So, in an unsteady flow problem, if I go back to a picture very similar to what we did in the convective inertia problem, so this was the convective inertia problem or the Oseen problem. This is the unsteady inertia problem. So, in the convective inertia problem, there was a length scale, a dimensional length scale, which was order, or if I just write it in terms of nu by u. So, within this the description was Stokes flow plus correction, and outside it was inertia competing with viscous effects. And that completely changed the flow field. If you remember, the flow field outside the Oseen region was composed of two separate regions. There was a source flow everywhere, and then there was a wake that was present. Here, if you similarly write down, there is a region which scales as square root nu tau, where tau is some intrinsic time scale, within which you can once again say that the flow is very well described by Stokes flow. So, you make any change to the boundary condition over a certain time. So, this comes back to the example problem I was showing. So, when you do this kind of an exercise where you say I am going from u1 to u2 over a certain time interval, you are introducing a time scale in the problem. I am accelerating for a certain period of time, and because I am accelerating over a certain period of time, I have introduced a time scale. So, in that particular time, within that particular time, for that particular time scale, I can construct a length scale within which the flow is very well described by Stokes flow. That means momentum diffusion is almost instantaneous in that region. So, the flow field in this particular region, if I am writing the velocity field, let us say in the lab reference frame for a translating sphere. So, what do you think would be the flow field? If I have this object moving with some velocity u bar of t, and there is an associated time scale by which u bar of t is changing. So, what should be the velocity field in that inner region? What should it look like? uj by 4 or 3 uj by 4, then there is a here, delta ij by r plus, and then delta ij by r cube minus 3 xi xj by r5. So, it is exactly a Stokes flow problem, but something that I have to pay attention to here is all these velocities are functions of time. So, within that region the velocity field will be given well described by the Stokes flow solution, even though there is a change. Now, how large is that region? That depends on what is the time scale associated with your motion. If you are saying that that intrinsic time scale that you are introducing into the problem is known, then automatically you can find out what that region is. Now, what do you think is going to happen outside that region? In the outer region, what is your guess about the flow field? Imagine this is the same problem, right? There is a sphere in a quiescent flow and you start to accelerate the sphere and the sphere's velocity is constantly increasing from 0. Which means that if there is a time scale over which the sphere attains a constant velocity, there is a region around the sphere within which you will see a Stokes flow solution. You are going to observe a velocity field which is going to look something like this, right. Now, what is happening outside that region? So, one way to think about this is think of it in terms of not just diffusion of momentum, but rather diffusion of vorticity. What was Stokes flow equation in terms of vorticity? What was the equivalent equation in terms of vorticity if you take a curl? If you take a curl of Stokes flow equation, del square omega is equal to 0. If you take a curl of the unsteady equation, you are going to get del omega del t is equal to kinematic viscosity mu by rho del square omega. So, what we are saying here is that in terms of vorticity, this region has a solution that is given by del square omega equal to 0. And outside this region, because the entire system is governed by this kind of an equation, what we are saying that outside this region, the fact that vorticity is diffusing from the particle surface. Any particle that is undergoing some kind of a motion can also be viewed as a source of vorticity. You can view it as a source of momentum, you can also view it as source of vorticity. So, any particle that is executing some kind of an unsteady motion is an object that is a source of vorticity moving in the fluid. So, within this region square root nu tau, you have the vorticity diffuse out almost instantaneously, but outside this region vorticity has not diffused out. So, if you have made any changes or if you have started the motion, whatever you have done, that has not propagated all the way beyond that region, which means in this particular region outside, the flow is well approximated by potential flow, because potential flow would be the flow where there is 0 vorticity. So, now you can think of that when you do this kind of an unsteady motion, if at rest the fluid was quiescent, as you make the object move, there is a Stokes flow solution surrounding the object. How much of a distance it surrounds? That depends on a screening length that is determined by the intrinsic time scale in the problem. Beyond that region, the flow remains well approximated by a potential flow. So, this is your inner region. I should put an approximation, these are all asymptotically correct, and in the outer region it should be close to a potential flow. Now, what is the potential flow due to a translating sphere? This part, that is the one we call potential dipole. This is the solution for a translating sphere in potential flow. So, this would be uj of t a square delta ij r cube minus 3xi xj r to the power 5, but there is a coefficient which we do not know, that has to be found by matching with the Stokes flow solution. So, this is the essence of what you would actually have in an unsteady problem. Stokes flow says you make any change to boundary condition, automatically all the way till infinity the information has propagated and the fluid until infinity has realized that you have made a change to your boundary condition, and it instantaneously adjusts to the latest boundary information. So, there is an infinite speed of propagation or 0 time scale relative to everything else. So, the viscous time scale is infinitely small, infinitesimal when compared to all other time scale. That is the idea of an instantaneous propagation of your momentum. Unsteady Stokes flow says that is not going to happen instantaneously. There will be a region within which you are going to observe a Stokes flow like solution, and beyond that particular region the flow is going to get modified, and that region beyond is where your information has not reached, that you have made a change to the boundary condition. So, this is the basic idea, and it is in as I was drawing the analogy with Oseen flow, that here too you have a screening length, and you have a screening length which is square root nu tau. Now, if you have a problem which is a problem of oscillation with a frequency omega, you can see this would be square root nu by omega. If you have a problem where it is accelerating over a period of time, let us say t star, then this would be square root nu t star. It depends on what you have introduced as the inherent time scale in this problem. Now, you are not really unfamiliar with this kind of an approach. In your graduate fluid mechanics class, you often do this problem where the problem of an impulsively pulled plate, right. There was fluid which was at rest at t equals 0, the boundary starts to move. So, u of t is some u bar in the x direction for t greater than 0. So, it was at rest and you accelerate it and bring it to a constant velocity immediately, it is an impulsive motion. So, you have done this calculation. When you do this calculation and you plot your velocity, let us say this is the coordinate y normal to the plate, and you plot your x velocity ux, the velocity at the plate is always 1, it has to be because of the no slip boundary condition. But then if you plot your velocity profiles, your velocity profiles are going to look like this. Gradually, more and more of the fluid realizes that there was a boundary that was set into motion. So, if you draw a particular level at any height y, what was the speed of the fluid at that location at an early instant of time, at a later instant of time it would have gained more speed, which means in terms of propagation of momentum or propagation of vorticity, it is penetrating further and further into the fluid. So, it is the same idea that is being done here. You did a problem in one dimensional Cartesian coordinate system. Right now, this idea is in the context of a spherical particle moving in a fluid. So, in terms of the underlying math, in terms of the underlying expectation of the velocity field, whatever you are going to get, you can already start to anticipate what will happen for the spherical particle. For instance, when you solve this particular velocity field, there are different methods of solving it. I am not going to go through the methods particularly. You use similarity variables, you use Laplace transform, etc. But one thing which you find in this velocity field is that you obtain a velocity that is expressed in terms of some function, right. And again, if you remember, this argument also comes from linearity. The governing equations are linear, the boundary conditions are linear, which means the velocity field should be linear in the plate velocity, and then you write it down that it should depend on the vertical coordinate and time in this manner, because there are no other additional time scales in this particular problem, length or time scale. Now, if you did not have this problem of impulsively pulled plate, you rather did a problem where the plate velocity, if I say u bar of t is the plate velocity, the one that you have done in class is this. At t equals 0, suddenly it switches to some constant value and stays at that constant value. But you could also do problems where it does all different kinds of protocol. It is accelerating uniformly, it accelerates uniformly and then switches its acceleration, it can have a non-linear acceleration. All these things are possible, right. You can do all these things with a plate, you can make the plate move with different velocity. When you do all of that, the velocity field that you are going to obtain will involve an integral over the plate velocity. The problem that you do in class, because in the problem done in class, it is an impulsive motion. You suddenly bring it to a constant velocity and then make it stay in that velocity. So, what is the acceleration in that problem? What is the plate acceleration? When is it infinity? So, at t equals 0, there is a jump in velocity, which means at that instant the velocity, the acceleration is infinitely large, u prime of t is infinitely large, and then it remains 0. So, this is basically in the class problem, this is actually a delta function. But you do not need to have a delta function, you can have all kinds of other functions in the problem, you can have all kinds of plate motion in the problem. And the interesting thing that you will observe here is that the velocity field is not dependent entirely on the plate velocity at that instant of time. The velocity field cares about how you have arrived at that instant of time. So, for instance, in the same plate problem, if you go back and do this exercise, the methods are in some sense very similar to what I will discuss today, but the final answer that you are going to get, that final answer would actually involve integrating over all your past acceleration. So, if you were to find that what is the fluid velocity, where in one case, so this is case 1, case 2, case 3, case 4. So, in one case you did the impulse problem, the typical class problem. In another case you did a constant acceleration and then you switched off the motor. In the third case you did a constant acceleration and then you suddenly changed the acceleration to another constant value and you turned off the motor. And in the last case you are constantly increasing your acceleration. The acceleration is not a constant. So, all these 4 cases would not give you the same fluid velocity if you choose to find it at a given instant of time. even though the plate is moving with the same velocity at that point in time. The plate velocity has not changed. The plate velocity is identical for all the 4 cases. But then at that point in time, whatever is the fluid velocity, it cares about your acceleration history. How have you ended up arriving here? And this is the key point of the unsteady term. That when you have the unsteady term in your momentum equation, the fact that there is no instantaneous diffusion of momentum, there is a certain distance over which only momentum can propagate, that makes it important for you to acknowledge that if there are different protocols by which boundary conditions are going to change, you are going to arrive at different answers. So, if you are measuring, let us say, the shear stress on the plate, the same one dimensional problem, you try to measure what is the shear stress on the plate. The shear stress on the plate, when you do the calculation for the class problem, this goes as square root T. It keeps decaying. The plate shear stress is constantly decaying as 1 by root T. But if you do the acceleration problem, you do the non-uniform acceleration problem, the plate shear stress will not be 1 over root T. So, how much you are experiencing as the shear stress on the plate actually depends on how you have arrived at that particular plate velocity. Did you do a constant acceleration? Did you do an impulse? Did you do a deceleration and then maybe an acceleration? So, every change of boundary conditions protocol leads to different response in the fluid and thus different forces on objects. So, with this description, what you can expect right now by doing all of this is the force when you are going to calculate. The force is obviously going to be a linear function of velocity. That is not debatable. We are not going to debate on the fact whether force depends linearly on velocity. Why aren't we going to debate that? We are still solving a linear equation with linear boundary condition. So, the force is not going to change in terms of its dependence on velocity. But because the velocity itself can be a function of time, what we are going to say that the dependence of force on time, this is not guaranteed. Stokes flow tells us that the force right now depends only on the boundary motion right now. That is what Stokes flow solutions are. When you include the unsteady effect, this is going to break down. That's the, even if you don't follow all the algebra that I'll probably try to summarize right now, this is the point which you should keep in mind, that unsteady effects are responsible on things like velocity field, drag forces, etc., depending on the entire history of motion.